Ka and Kb are dissociation constants of acids and bases. Their magnitude allows us to compare between strong and weak solutions of either acids or bases. Let's start with acids. Strong acids have very large Ka values. Examples of strong acids are shown here. Weak acids, on the other hand, very small or low values. The bigger the Ka value, the stronger the acid. Ka can be calculated from the reaction of the acid, either dissociated as being shown here, simply breaking apart into the hydrogen ion and A-, its conjugate base, or it can be evaluated from the reaction of the acid with water or ionizing with water to produce the hydronium ion and the conjugate base. Both expressions use the same value, meaning you can use either equation to describe the behavior of an acid. Strong bases, things like sodium hydroxide and potassium hydroxide, also have large Kb values, and weak bases very low Kb values. The reaction for bases should be viewed the following way, where the base accepts a proton from the water molecule and forms BH+. Let's now consider a simple conjugate acid-base pair and their reactions. So I'm going to take my weak acid and have it dissociate into H+ and the conjugate base. That conjugate base can then react with water to produce the weak acid and the hydroxide ion. These have equilibrium expressions, here for Ka and here for Kb. Because many acid-base solutions are made with water, one should expect that the equilibrium holds true for water solutions. Anything that's made in water should follow this ion product rule. This equation is in our IB data booklet. I'm going to take the Ka expression from above and rearrange it to get the hydrogen ion by itself. In a similar fashion, I'm going to rearrange the Kb expression to get the OH ion by itself. So if we substitute these in, we get the following. Notice what cancels. The weak acid will cancel and its conjugate base, leaving us just Ka and Kb. This equation is also in our IB data booklet. By taking the negative logarithms of both sides, the p operator, we get the following. This expression is not in our IB data booklet, but worth memorizing. In many cases that you work with, pKw will be 14, provided the temperature is 25 Celsius or 298 Kelvin. Let's solve a few questions that have these in them. First off, I want to determine the pH of a 0.1 molar ethanoic acid solution, whose pKa is 4.76. From that 4.76, I know what Ka is. Also, I know ethanoic acid. I'm going to write down the equation for it, dissociating. Let's bring in an ice table. The initial amount of our ethanoic acid is 0.1 and 0 and 0 for the other two. I'm going to assume that the ethanoic acid will go down by x and hence the others both up by x. So I now have the following at equilibrium. Now what do I have for the equilibrium of the ethanoic acid? Well, actually 0.1 minus x. But noticing that Ka is a very small value, I can make the following simplifying assumption. It avoids the quadratic equation by doing this. Substituting now in for the Ka expression, I get the following. Notice I'm leaving things as power of 10, and you'll see why when we solve. So isolating now for what x squared is equal to, and now because I've left it as an exponent, I can take the square root of both sides. I just have to divide that exponent by 2. And that gives me 10 to the negative 2.88. Since I want the pH of the solution, I take the negative log of that number and get 2.88. In a follow-up question to this, the solution containing the ethanoate ion has a pOH of 6.4. Determine the initial concentration of the ethanoate ion. So this question is a follow-up from the previous one. So I am going to reach back and grab some information from it. First thing I'm going to write is the equation for the ethanoate ion acting as a base. So here it is accepting the proton from water to form the weak acid in the OH ion. And I'll put in my ice table. Now, from knowledge that the pOH is 6.4, I can say that at equilibrium, the concentration of the OH ion is 10 to the negative 6.4. That allows me to fill in all the other bits of information. Notice that the change in the ethanoate ion concentration is a very small number, so I can make this simplifying assumption for it. But what we need now is what's pKb, or Kb for this reaction. For that, I'm going to turn over and use some information from the previous question. pKa plus pKb is going to equal pKw. I'm going to assume that this reaction is at 25 degrees Celsius, so that total is 14. And I have pKa from the previous question. Now I can solve for pKb. That means that Kb, the equilibrium constant, is 10 to the negative 9.24, a very small number that also justifies making my assumption. Substituting now for the Kb expression, I'm going to now expand it and then solve for x. So 2.8 times 10 to the minus 4 moles per decimeter cubed. I hope you found that worthwhile. If you have any questions, don't hesitate to ask. Thanks for watching.